Precision Measurement for Machinists, a MasterTask multimedia program. Lesson 6, Using Calipers and Go, No-Go Gauges. When measuring dimensions of varying lengths, calipers are very useful and versatile tools. As you learned in the last lesson, micrometers can make precise measurements, but are limited to a relatively small measuring range. Calipers can allow a larger measuring range than that of a micrometer. In this lesson, you will learn to measure workpiece dimensions with either dial or vernier calipers, as well as the use of digital calipers. You will also learn about go, no-go gauges. There will be 5 parts to this lesson. In Part 1, you will learn the components of vernier and dial calipers and the 3 types of measurement that can be made with a caliper. Part 2 will describe how to measure a workpiece using a dial caliper. Vernier calipers are covered in Part 3. Part 4 introduces digital calipers. And Part 5 will show you different types of go, no-go gauges and their uses. Part 1. Caliper measurements and components. There are 3 types of calipers: vernier calipers, dial calipers, and digital calipers. There are 3 types of measurements that can be taken with a caliper. Outside diameters and the length of surfaces are measured with outside jaws. At the end of the outside jaws are the knife edges used to measure grooves and slots where the jaws would be too wide. The second type of measurement uses the inside jaws, also called the blades. They can be used to measure internal surfaces and diameters. The third type of measurement uses the depth rod. It's used to measure the depth of holes, slots, and recesses. An optional depth attachment can be put on the caliper to ensure that an accurate depth measurement is taken. If you don't have access to a depth attachment for your caliper, be very careful when taking depth measurements. Make sure that the depth rod is kept perfectly straight and is perpendicular to the surface being measured. If the depth rod is inserted at an angle, the measurement will not be accurate. Some larger size dial and vernier calipers will not have depth rods. This is the beam of the caliper. It is found on all 3 types. The beam is graduated like the baseline on the sleeve of the micrometer. The largest division on this caliper is 1 inch. Each inch is divided into 10 small spaces. Each space represents a distance of 100 thousandths. For example, the distance between the small line marked 3 and the line marked 4 is 100 thousandths of an inch. There are also calipers that are graduated with a metric scale, or both the inch and metric scales, to take measurements in either inches or millimeters. This is the slide of the caliper. The slide rides along the beam. One side of the jaws and the depth rod are all attached to the slide. Observing the slide's position on the beam is the first step in how measurements are taken on a caliper. Because this caliper is equipped with a dial indicator, it is called a dial caliper. Each of the lines on this particular dial measure a distance of 1/1000th of an inch. The key on the face of the dial will specify the value of the smallest division on the dial face. There are differences in how dials are marked between different brands. This dial reads 0 to 100 thousandths in one rotation of the indicator needle. For each 100 thousandths measured, the slide will move past one small space on the beam, and the needle will make 1 revolution. Before a caliper can be accurately used, it is important to notice the number of divisions on the beam. For example, this caliper has each 100 thousandths divided into 2 50 thousandth spaces. Be sure you know what amount each space on the beam and each space on the dial represent when making a measurement. A metric dial caliper works the same way. The largest division on the beam is 1 centimeter. Each centimeter is divided into millimeters. 1 revolution of the dial on this metric caliper represents 2 full millimeters of movement of the slide on the beam. This is a vernier caliper. It can be used to measure the same workpiece features as the dial caliper, such as outside, inside, and depth measurements. You will notice there is no dial. Instead, there are vernier scales above and below the beam that can be used to read the most precise value in the measurement. The small graduations on the vernier scales allow measurements to 1/1000th of an inch or to 2/100ths of a millimeter. As it was on the metric dial caliper, the metric beam scale is divided into 1 centimeter units by each long numbered line. The 10 small spaces between each long line represent 1 millimeter each. Inch and metric vernier calipers are read the same way. While the edge of the slide is used to begin the measurement on dial calipers, the 0 line on the vernier is the start point when reading vernier calipers. The smallest division on the beam determines how many lines are on the vernier. Since this inch beam is divided into 25,000th spaces, the vernier will have 25 numbered lines. This inch vernier caliper has a different jaw design. The inner surface of the jaws are for outside measurements, while the outer surface is used for inside measurements. The vernier portion of the caliper has 2 vernier scales, one for outside and one for inside measurements. This is necessary because of the offset in the 2 jaw surfaces. Part 2. Measuring workpiece features with a dial caliper. When you're ready to begin measuring workpiece features with any caliper, the first thing you must do is make sure the caliper is operational and properly adjusted. First, check the caliper for dirt and grit. If necessary, clean the caliper. Also, thoroughly inspect the contact surfaces of the jaws. If there is any dirt or grit present, remove it. Look for any nicks or other defects in these surfaces. Damaged jaws will affect the measurement. If you suspect the caliper may be damaged, use another instrument. Second, move the slide up and down the beam to check for smooth movement. Next, check the dial and make sure it is performing properly as the slide moves. To check for a proper adjustment, first move the slide along the beam so that the jaws are completely closed. Now check the measurement. The reading should be exactly 0. A reading other than 0 indicates the need for calibration. On this dial caliper, the dial face clamp screw is loosened. Then the dial is rotated to 0 the dial reading. Then the clamp screw is tightened. Now that you have determined that your caliper is in working order, check the workpiece feature to be measured. Make sure the workpiece is free of any dirt, grit, or oil. Use a shop cloth or rag to clean any debris off of the workpiece. Fitting the calipers to a workpiece requires the same care as when using other measuring instruments. Use the thumb wheel to adjust the final position of the slide. Applying too much pressure can damage the caliper and provide incorrect measurements. Rotate the workpiece to find the true diameter. If the knife edges are used for measurement, be sure they fully contact the surface. Once the feature is correctly measured, snug the lock screw and remove the caliper. Reading the measurement also requires care. On this dial caliper, count only the complete spaces on the beam to the left of the edge of the slide. When reading the dial, count only the complete spaces the indicator needle has passed. Do not read past the indicator needle to the next line. In this example, the slide of the caliper has gone past the first whole inch mark. Therefore, the number to the left of the decimal is 1. The edge is past the 6th small space on the beam, and since each space represents 100 thousandths, the measurement is 600 thousandths. The indicator needle is located just past the line for 34. 34 times 1,000 is 34 thousandths. Using the standard rules for addition of decimal numbers, add the reading from the 3 steps. The measurement taken is 1 inch 634 thousandths. Write down this measurement and compare it to the nominal dimension on the print. The same procedure is used when measuring with a metric dial caliper, only the calibrations on the beam and dial are different. While metric prints often state measurements in millimeters, metric calipers often have the beam marked in centimeters. Add a 0 to the centimeter value to convert it to millimeters. This dial is different than other calipers. Notice that it has a second 0 point at the bottom of the dial. 1 complete revolution of the needle represents 2 millimeters, 1 millimeter for each half of the needle rotation. Each numbered line represents a distance of 0.1 millimeter. Each small space between the numbered lines represents 2/100ths of a millimeter. In this measurement, you see that the number of whole centimeters is 10, which is 100 millimeters. The small divisions are 1 millimeter each, which is 4. So the total from the beam is 104 millimeters. The needle has not passed the bottom 0 point, so the value to add is 0.4. Therefore, the total is 104.4 millimeters. In this example, the beam reads 2 centimeters or 20 millimeters, plus 7 spaces for a total beam reading of 27 millimeters. Notice that the needle has passed the bottom 0, indicating how far past the 7 whole millimeters to read the measurement. The numbered spaces past the 0 are 0.3. Each small space past the 0.3 line on the dial represents 0.02 millimeter, so for 3 small spaces add 0.06. Therefore, the dial totals 0.36 millimeters. Add the beam and dial totals to get 27 millimeters 36 hundredths. Rules of maintenance and care that apply to other measuring instruments also apply to dial calipers. Clean, lubricate, and store the calipers in their proper storage cases and in the tool box or tool crib after you have finished using them. Part 3. Measuring with a vernier caliper. This caliper has a vernier scale mounted on the slide instead of a dial for taking measurements precise to 1/1000th of an inch. Measurements taken with a vernier caliper are just as accurate as measurements taken with a dial caliper. However, reading a vernier caliper can be more difficult. The most difficult part of reading the vernier caliper is to identify the line on the vernier scale that lines up with the line of the beam scale. Once the matching line is found, remember to read the number on the vernier scale as the measurement value. To verify that the lines match, look at the lines on either side. Each line should be slightly inside the line opposite. The next pair of lines will be offset further in the same direction. On this caliper, each inch is divided into 10 spaces by the small numbered lines. Therefore, the space between the small numbered lines is 100 thousandths. The distances between the 100 thousandths lines are divided into 2 smaller spaces. Each space represents 50 thousandths. Therefore, there are 50 lines on this inch vernier scale. Each of these lines represents 1/1000th of an inch. Therefore, this caliper is precise to 1/1000th of an inch. When taking a measurement, the vernier scale 0 mark will be just to the right of the closest 25 thousandths graduation on this inch beam. The 0 line on the vernier scale always serves as the start point of the measurement. In this example, the 0 is just to the right of 3 inches, 125 thousandths. Now look closely at the vernier scale and find the graduation mark that lines up with one of the lines on the beam. There can be only one. You see that 7 on the vernier matches most closely the graduation mark on the beam below. Therefore, 7 is the number of thousandths of an inch. Be sure to move the caliper directly under your eye to be sure a parallax error does not cause you to select the wrong line. To make sure you are taking the proper reading, look at the 6 and 8 lines on the vernier. Both graduation marks should be closer to the 7 than the corresponding graduations on the beam. Add the vernier value of 7 thousandths to the beam value of 3 inches, 125 thousandths, and you will have a total measurement of 3 inches, 132 thousandths. Let's look at another example using the vernier caliper. In this measurement, there are no large numbered lines to the left of the 0, which means there are no whole inches. The slide has passed the 6th numbered space, which is read as 600 thousandths. There are 3 of the smaller spaces between the 6th line and the 0 line on the slide. 3 times 25 thousandths is 75 thousandths. Since the matching vernier line is near the 0, you may need to look at the other end of the scale to check the offset of the other lines. In this measurement, the line which most closely matches the line on the beam scale is the number 2 on the vernier. Add the 3 measurements together. Keep the decimal points in line in order to properly identify the thousandths place. The measurement taken was 677 thousandths. Many vernier calipers have both inch and metric graduations for reading either inch or metric measurements. On this vernier caliper, the inch graduations are on the top of the beam and the metric graduations are on the bottom. In this example, we will be looking at the metric graduations of the caliper. You see that the graduations on the beam start at 0 and are numbered every 10 spaces. This is the number of whole centimeters. Now look at the graduations between the whole centimeter marks. These represent whole millimeters. Now look at the metric vernier scale. Each graduation on the metric vernier represents 2/100ths of a millimeter, or 20 microns. Therefore, this caliper is precise to only 2/100ths of a millimeter. Begin by reading the number of full centimeters and convert it into millimeters. In this example, the number of whole centimeters is 4, or 40 millimeters. The number of whole small divisions on the beam is 5, so the total beam reading is 45 millimeters. Now look at the vernier scale. Find the line on the vernier that lines up most closely with a line on the beam. Remember, there can be only one. In this example, this line on the vernier matches up exactly. The last numbered line on the vernier is 4, so the first number to the right of the decimal is 4. Since each vernier space represents 2/100ths of a millimeter, 4 times 0.02 equals 0.08. Once you have determined the proper vernier reading, add the measurements together. The final measurement is 45.48 millimeters. Because of the large number of lines on the metric vernier, it can be difficult to tell which line matches. In this example, both the 0.52 and the 0.54 lines appear to match equally. You might be tempted to read this as 0.53. Since a line representing 0.53 does not exist on the vernier scale, this value cannot be used as a measurement. The precision of the instrument is limited to the markings on the vernier. To decide whether the 0.52 or 0.54 should be used as the measurement value, look at the relative location of the value. If the measured value was near the upper tolerance limit, then use the upper value. If the measured value was near the lower tolerance limit, use the lower value. In this example, if the total value were near the upper limit, use the 0.54 value. If the total measurement were near the lower limit, the 0.52 value would be used. Always use the value which is least favorable to be sure no dimensions are ever over or under the tolerance specified. A magnifying lens can be used to more easily locate the matching lines on a vernier. Part 4. Digital calipers. Digital calipers typically make reading measurements easier. However, they are usually more expensive than dial or vernier calipers. The main feature of a digital caliper is the display on the slide. Instead of a dial or a vernier scale, an electronic digital readout of the measurement is displayed in an LCD window. These LCD displays are typically powered by a battery. To conserve battery life, most digital calipers will automatically turn off power within a period of time after the slide stops moving. Be sure to note the measurement before the caliper turns off. Most electronic calipers can display measurements in inches or millimeters. This can be a powerful tool for converting measurements from one system to another. For example, if you have a measurement of 12.35 millimeters and need to know the inch equivalent, simply press the inch-millimeter button, and the inch measurement of 486 thousandths will appear in the window, replacing the metric measurement. Another feature of many digital calipers is the ability to zero the caliper at any position. If you are measuring many identical workpiece features, you can set the caliper to 0 at the nominal size the feature should be, and then determine how much larger or smaller each actual workpiece is than the nominal dimension. Remember that using this feature will require you to work with signed numbers. Part 5. Go, no-go gauges. Frequently, one or more dimensions on a workpiece will be a critical dimension. These dimensions will be the ones that establish whether or not the part will meet production tolerances or allow assembly with other components. Go, no-go gauges are used during production situations. They allow the operator to quickly check the dimensional accuracy of a feature. There are two key parts to all these gauges: the go end or block, which will fit a correctly machined feature, and the no-go end or block, which will not fit a correctly machined feature. There are many different types of go, no-go gauges. This is a snap gauge. Snap gauges have inside measuring surfaces, and are made to measure diameters, widths, and thickness. A workpiece within manufacturing tolerances will enter the go opening of the snap gauge, but will not pass the no-go opening. The go opening is the nominal dimension plus the upper tolerance allowance. A workpiece that will not enter the gauge is oversized. The no-go block is the nominal dimension minus the lower tolerance. A workpiece that will enter the gauge and pass through is undersized. This is a functional gauge that uses go, no-go plug gauges to check the ability to assemble with other components. The workpiece, a stamped hinge in this example, is mounted to the gauge over the locating pins. The piece is then clamped into position. The go gauge then checks for undersized holes and location. Plug gauges can also be used to check the roundness and straightness of holes. This go gauge is machined to 496 thousandths in diameter. The no-go end of this gauge indicates it is machined to 501 thousandths in diameter. Fitting the plug gauge to the workpiece requires care. Always be careful not to force the plug into the workpiece. Ring gauges are used to check the outside diameter of a workpiece that is cylindrical in form for manufacturing tolerances. Before measuring, be sure to clean the gauge and the workpiece. There is a separate gauge for no-go tolerancing. The no-go ring gauge is machined with a groove outside the ring for easy identification. Long parts should be passed all the way through the gauge. This will check the workpiece for tapers and for straightness. A go, no-go gauge only demonstrates whether a feature passes or fails a specific dimensional check. It does not indicate by how much the feature failed the test. Therefore, if a part fails the go, no-go test, other measuring instruments must be used to find out what is wrong and how much to adjust the manufacturing process to correct the problem. This completes your video instruction on analog and digital calipers and go and no-go gauges. See your instructor regarding your next step.